Before we jump into the next part of Chapter 5, we're going to go back over the two sections that we went over before the break. So this note sheet here is really just running through some of the stuff that we did and going through a few of the properties. Now, the first thing we actually covered before or in Chapter 5 is rewriting these radicals in exponential form and as a rational exponent. And the general form for any of these here come in the form of the nth root of a to the x is equal to a to the x over n. So we can rewrite any radical as a fractional exponent in this way. So when we look at the first one here, the cubed root of x to the fourth, well, we can rewrite this as x to the what? 4/3. Because since the root is 3, it goes on the bottom of the fraction, and the exponent inside the radical with our variable here, x, would go in the numerator. Clear this down. So that would actually be the final answer, x to the 4/3. Now, when we look at the second one, we have the fifth root of x times y squared. Now, we can apply it to both our x, y squared, and we could say that this is to the, well, the bottom of it would be 5, because that's our root. But what would the numerator be? 1, because since we talked about it as a whole term, we would do it this way here. Now, we could have skipped this step and really just said that we apply it to both. So it'd be x to the 1/5 and y to the 2/5. So we could have done it individually. We didn't have to do it as one term. Yes, sir. Yes. So we could have gone straight from the radical form to x to the 1/5 times y to the 2/5, and that would be the exact same thing. And the last one that we have for the first three is the fourth root of x squared, right? Because we'd say x to the 1/2, or because we could rewrite it as x to the 2/4, but 2/4 will reduce to 1/2. So those would be our answers. And it does work out that the fourth root of x squared and the square root of x are actually the same thing. Any questions on this here? Well, the next three are just going the other way around. They gave us it as a fractional exponent, and we want to rewrite it in radical form. So the first one we have is x to the 2/3. So if we're going to rewrite it as a radical, well, we would have x inside. And our root for this here would be 3. Because the denominator of the fractional exponent would be the root. And what goes inside with the x would be the 2. Now we look at number 5, we have y times z all to the 4/5. Now we can say that we do have y times z together inside the radical. Our root would be 5 because it's coming from the denominator, and the y times z would be to the 4th. Now we could have also said that this here is the fifth root of y to the 4th times z to the 4th, because we can apply that power of 4 to both the y and the z inside the radical. Either one of those would be the same answer. And lastly, we have x to the 1/2. So we're going to have our radical, and we'll have x inside. And what number goes in our root? 2. Do we have to write the 2? No, because if we have a 2, it's telling us that we're taking the square root. With radicals, if there's not a number written, it's understood to be 2. And our exponent with x would be 1, which we don't need to write. So actually, x to the 1/2 is just the square root of x. Any questions on 1 through 6? Seven through 12, we're going to evaluate each of these to the nearest third decimal place if needed. We may not need to. Because number 7, the cubed root of 1728. So we could say 3 second our x root 1728. And we get 12. So we don't even have to round. We could have also done this in radical or as a rational exponent. 17, well, not 8, 28, and say that this is to the 1/3. Because we could have written it as a fractional exponent and actually gotten to the same thing, which for some of the roots it might be easier to get to than trying to get to the cubed root. So for us here, number 7 is 12. (26, 21, 44). So we're going to take the 9th root of 26, 21, 44. To the 1/9, and it actually works out to be 4. So now we can do simplify 81 to the 1/4, which is 3. Because again, we're just typing these in the calculator. How about 16 to the 5/2? 1024. For which one? You worked ahead for number 11. What'd you get? Okay. Probably 0 point. 1.87. One more. 3. Yeah. And that one is expected to give us a decimal answer. Because we're looking for what number times itself 2/7 of a time gives us 9. And well, 9 is rewritable because we could rewrite 9 as 3 squared to the 2/7. And powers of powers multiply, which is really just telling us that we have 3 to the 4/7. That doesn't get any simpler than that. So we're going to end up with a decimal. Now with the previous ones like 81, well 81, I could have actually rewritten this as 3 to the 4th to the 1/4. 4 times 1/4 is just 1, which gives us 3. So all the ones before that we got a whole number is because they're actually reducible. Number 11 isn't. And most likely, number 12 is not either. What do we get for 12? And that's kind of a given since 17 is a prime number. We can't take square roots or eighth roots of a prime number unless for some reason our exponent is also 8, or they cancel out. All right, for 13 and 14, we want to find the value or values of x. So we need to solve. And when we solve these here, we're really doing the same thing we did for the square root method, trying to get the variable or set of parentheses to the exponent by itself, and then taking the root. Well, for number 13, we have 1/9 times x to the 6 is equal to 1265625. Well, we need to get rid of the 1/9 first. And there's two different ways we could do it. What's one way that we can get rid of the 1/9? Well, we can multiply both sides by what? We wouldn't use 1/9, but we can just use 9, because we can multiply by the reciprocal of a fraction, because 9 times 1/9 would be 1. We could have also divided both sides by 1/9. And we'd actually get the same type operation. We have x to the 6 is equal to 5 carry the 4, 18. 2 carry the 2. 54, 56, 45, 50. 9, 5, 18, and 20. 11,390,625. Huh? Okay. And well, any questions on how we got to this point here? Now, at this point here, we do need to get x by itself. So we're going to apply the 6th root to both sides. And we do have to be careful when we take the 6th root of both sides, an even root of both sides. Because if we take an even root and what's inside the root is negative, we don't have any real solutions.
Do you have any tissue?
No, I don't. You can go to the bathroom if you need. So if we take the even root and what's inside here is negative, we don't have any real roots. And for most of this chapter here, we're going to mainly focus on the real roots, not finding the complex. Now, if it's 0, well, we have exactly one root, and that would be 0. And if what's inside here is positive, we have two possible roots. We have the positive and negative of that case. So for this here, we're going to have to add the plus or minus. And it works out that the 6th root of this number here is 15. That is quite a big number to simplify down to 15. But we are also multiplying 15 by itself 6 times. So it is expected to get pretty big. Let's look at number 14. 14, we have x plus 3 to the third. Now, there are two different ways we could go about this. One of them is multiplying x plus 3 by itself 3 times, and then trying to simplify that cubic. But, well, since x plus 3 is already by itself, and it's to the third power, the easier way is just to take the cubed root of both sides. Because the cubed root of x to the third these simplify out. And now we just need to find the cubed root of 5,832, which is 18. Now with cubed roots, we did have 3 different cases, just like with the even roots. Whenever we have an odd root of a negative number, we have one real root. And whenever we have the odd root of 0, we have one real root. And whenever we have the odd root of a positive number, we have one real root. So with odd roots, so cubics, we don't have to add the plus or minus because no matter what's inside the odd root, we only get one. We only have one real root. which just leaves us with our last step of getting x by itself. So we would need to subtract 3 from both sides, telling us x is equal to 13. A whole lot of 15s. We finish those problems at the 15-minute mark. Now for the rest, most of the rest of these here, we're really going to be looking at simplifying these different rational exponents. Now the first one that we have here is 3 to the 1/2 times 3 to the 1/3 to the 6th. And there's different properties that we can use. One of them is our multiplying like bases, because since I have 3 to the 1/2 times 3 to the 1/3, we can add the exponents together. We also have our power of a product. Because of the 6 outside, we can multiply to both of the exponents on the inside. And it doesn't matter which one we do first, because we'll end up with the same thing. It might be easier to apply this 6 to both of these first before we add the exponents. Because 1/2 plus 1/3 is not a nice addition. Let's see what happens if we multiply. Because here we'd have 3 to the 1/2 times 6 times 3 to the 1/3 times 6. See the highlighters. So our first one here, 1/2 times 6 is 3. 1/2 times 6 would be 3 times. In our other one, we have 1/3 times 3, or 1/3 times 6, which is 2. So here it actually worked out using the power of a product. Multiplying that in actually made it easier to work with, because instead of having 2 fractions, we now have 3 and 2. Whenever the bases are the same, we can add the exponents. So it'd be 3 to the 3 plus 2, which is 3 to the 5th, which we can simplify, because at that point here we can just type that into the calculator. 3 to the 5th would be 5. And that right there would be our final answer. Any questions on this first one here? Okay. We can look at the next one, 16. 5 to the 2/9 over 5 to the 1/3 to the 9th. Now, since we do have like bases being divided, we could subtract the exponents. So we could subtract 2/9 and 1/3 to see what we get. But it does work out that both of these are to the 9th power. Multiplying 2/9 by 9 would simplify to a whole number. Would multiplying 1/3 by 9 simplify to a whole number? So let's try doing that. So if we use our power of a quotient, it would give us 5 to the 2/9 times 9 over 5 to the 1/3 times 9. Well, the numerator, 2/9 times 9 is 2. And in the denominator, 9 times 1/3 is 3. Now at this point here, we can subtract the exponents. So that would tell us that we have 5 to the 2 minus 3. And 2 minus 3 is -1. Unfortunately, we can't leave the exponents negative. We have to get them to stay positive. So to get the exponent positive, we move it from the numerator to the denominator. It becomes +1, or just giving us 1 over 5. Now, ways we've done this before is looking at 5 squared over 5 cubed. We can subtract the exponents. 3 minus 2 is 1. Was it bigger on top or bottom? It was bigger on bottom, so it stays on bottom. And that's another way to do the same type operation. Any other questions on this here? All right. Let's look at 17 and 18. 17 is 4 to the 5th times 3 to the 5th to the -1/5. Well, kind of like we did in the last one, or one of the last ones. We can go on and apply the -1/5 to both of these here. So that would give us 4 to the 5 times -1/5. If you can see what that already reduces to, you can go on and reduce it. We don't have to rewrite it back out. But if you need to, we can go on and say that this is 4 to the 5 times -1/5 times 3 to the 5 times -1/5. Well, 5 times -1/5 is just going to be -1. And it'll work out for both of these here. So we end up getting 4 to the -1st times 3 to the -1st. Questions on this here? Well, again, we can't have negative exponents, so they got to move from the numerator to the denominator. Both of them do, so we end up just getting 1 over 4 times 3. And 4 times 3 is, so we have 1/12. And I think some of these here, the calculator can do it for us, but it is nice to see how it works by hand. That way we know how to do it, just in case we hit one that doesn't. Let's look at number 18. So we have 18 to the 1/4 divided by 9 to the 1/4, all of this to the 3rd. Now what we really need to simplify out of this is the fact that the fraction in the denominator. And we can't have a fraction in the denominator or a fraction inside of the radical, or have a fractional exponent with a fraction. One of the things that is interesting is 18 and 9, are they divisible? So what we could say is that this is, well, if it'll not do the weird scrolling, that this is 18 over 9 to the 1/4 to the 3rd. Well, 18 divided by 9 is 2. So we did that so that we could actually divide those two there and simplify it a little bit easier. The other way was one that we'll look at here in a minute, is trying to simplify that radical in the denominator. And here, since the numerator and denominator will divide, we'll pull that fractional exponent out. And we can especially do that since both the numerator and denominator were both to the 1/4. Since they're both to that same rational exponent, we can pull it out. Now at this point here, we just need to multiply them together. Well, 1 times 1/4 times 3 is 2 to the 3/4. Because really we're looking at 3 times 1/4, and 3 times 1/4 is 3/4. Now with some of these here, we can always try typing these in the calculator to see if it does simplify out. Because if it does, that makes it even easier to work with. So we could try typing in the third root of 12 times the third root of 18 and see if we get a number. Because if we look at 12, 12 we can say is 3 times 4. Well, 4 is 2 squared. So 12 is 3 times 2 squared. 18 is 2 times 3 squared. If we wrote this out as in prime factorization, because our 2 times 3 squared is really 2 times 9. 2 times 9 is 18. We just simplified them down. And if we multiply these together, because we can multiply the numbers inside, we'll have 2 squared times 2, which is 2 to the third. 3 times 3 squared is 3 to the third. If we take the cubed root of 2 to the third, we get 2. If we take the cubed root of 3 to the third, we get 3. And 2 times 3 is 6. So it works out that this one does simplify completely. Well, then the next one we can look at is 20. So we're looking at the fourth root of 80 divided by the fourth root of 5. Now we are able to divide 80 by 5, so we could put that back together and say that we're looking at the fourth root of 80 divided by 5. And if we divide 80 by 5, we get 16. So now we're just really seeing, can we take the fourth root of 16? We can, it is 2. Really what we're saying is that the fourth root of 2 to the fourth is 2. So these first two here do simplify nicely, and we could have actually typed the second one into the calculator also, and it would have told us that it is 2. Now the next one, 21. We're looking at the fifth root of 7 divided by the fifth root of 8. Well, I know I can't take the fifth root of 7 because it's prime. 8 is not prime. It would do that. But I can rewrite 8 as 2 to the third, because 2 to the third power is 8. And we could have done a factor tree to get there. But what that tells me is that the numerator and denominator won't simplify nicely. I'm going to need to find a way to get the denominator to simplify nicely. Well, how many 2's would it be nice to have to get this fifth root to go away? We need 5 total. We have 3. I'm missing how many? 2. So what we can do is multiply the numerator and denominator the fifth root of 2 squared. Because if we multiply top and bottom by the fifth root of 2 squared, the denominator becomes the fifth root of 2 to the fifth. I've got 5 of them in the denominator, and that fifth root and fifth exponent will simplify. Now the numerator, I have the fifth root of 7 times, well, 2 squared is 4. Since I know 7's prime, I don't have enough 2's to simplify that root in the numerator. I'm just turning it back into 4 because we're going to end up multiplying it all together. And the fifth root of 2 to the fifth is 2. The numerator, well, 7 times 4 is 28. So we end up with the fifth root of 28 over 2. Any questions on this here? All right. that brings us to the next two. These here, I think y'all liked a little bit more than the others, because our first one, 1 over 2 plus the square root of 2. Over 2 plus second square root 2. The TI-30XS's will actually do these for us. Because when we went through this the first time, we talked about multiplying by the irrational conjugate. We changed the sign between the two numbers in the denominator and multiplied it on top and bottom. So for us here, it'd be just saying that we're multiplying top and bottom by 2 minus the square root of 2. And for our numerator, 1 times 2 minus square root of 2. So I'll just 2 minus square root of 2. When we multiply the denominator, our 2 times 2 gives us 4. 2 times negative square root of 2 is negative 2 square root of 2. 2 times square root of 2 plus 2 square root of 2. And then we would have minus square root of 2 squared. We're just going to say 2 minus square root of 2. Our middle two terms cancel. This term just becomes 2. And 4 minus 2 is 2, which is the exact same thing we got in the calculator. Just a lot less steps. We can do the same thing for our next one. Okay, second square root 2 minus 1 over second square root 2 plus 3. 4 square root of 2 minus 5 over 7. The calculator likes putting the radical first, but that's perfectly fine. Any other questions on 22 or 23? Let's look at 24, 25, and 26. Well, if our radicals or our terms are the same, we can add or subtract. So at 24, we have 7 fifth roots of 12 minus 5 fifth roots of 12. Since we both have the fifth root of 12 in both of these here, we can subtract our coefficients, telling us that we have 2 fifth roots of 12, because 7 minus 5 is 2. Number 25, 4 times 9 to the 1/3 plus 8 times 9 to the 1/3. Because these are the same. Number 26. So we have the third root of 5 plus the third root of 40. If we're going to be able to add or subtract, we need them to both be the same. Well, I know I can't take the third root of 5 any further than it is because 5 is prime. But 40, we need to see if we can rewrite it as some number times the third root of 5. So hopefully there's a number that when multiplied by 5 does give us 40, and that number we can take the cubed root of. Well, what times 5 is 40? 8. So we have 8 times 5. So the big question is, can we take the cubed root of 8? Yes, it is. So the cubed root of 5 plus 2 times the cubed root of 5 is 3. Cubed root of 5. And whenever we're doing these here, we're just trying to see, can I rewrite it so that the radicals are the same? Any questions on this here? All Let's look at 27, 28. Next. Now, when we look at these here, we're wanting to reduce these radicals if possible. So for number 27, we need to see, can we take the fourth root of 256? Yes, and it is. So we can say 256 to the 1/4 is 4. So we can type 256 to the 1/4 to see if we can simplify this radical. Now we also have y to the 8th. So we're trying to see if we can take the fourth root of it. And we can, because we're really just saying that we have y to the 8/4. And 8 divided by 4 is 2. So this here would be the final answer that I would take. And we don't need absolute values for this one because y squared is still going to be positive. We don't have to worry about a negative case. Any questions on 27? Now 28, when we looked at this here, because we're taking the 9th root, so really we're dividing each exponent by 9 and simplifying accordingly. So for the numerator, x to the 9th, we're really saying that we have x to the 9/9. In the denominator, we have y to the 18/9. Because we're dividing each of those exponents by 9. Well, 9 divided by 9 is, so we just have x. 18 divided by 9 is 2. So this would just simplify x over y squared. And that would be our final answer. Questions on this here? Now we look at 29 and 30. With 29, we're trying to take the cubed root. Now, can we take the cubed root of 4? No. We can take the square root of 4, we just can't take the cubed root. So if we're looking at this here, well, I'm going to need the radical, our cubed root of 4, because 4 can't reduce, it can't simplify out, so it's just going to stay there. Can we take the cubed root of x to the 6th? 2. It'd be x squared, because off to the side we can say x to the 6/3. 6 divided by 3 is 2. It does simplify out completely. Or really we can look at pulling out groups of 3. Well, with 6 I can pull 3 out of 6 twice. We have none left over. Y to the 8th, we can do the same thing. We can say y to the 8 divided by 3. Right, it would only go in twice. Which would be 2 and, because 6, 2/3, y squared. Or we can look at it as pulling out groups of 3. We can say 8 minus 3 is 5. Minus 3 is 2. I can't pull 3 out any further. So we have 2 left inside, and we pulled 2 groups of 3 out. Z to the 4th. Well, with our subtraction, we can say 4 minus 3 is 1, yes? So we can pull one group of 3 z's out, and we have 1 z left over inside. So that there is the final answer. Let's look at 30. So we do need to simplify the cubed root of y to the 8th in the denominator. Now, can we take the cubed root of y to the 8th evenly? Well, 8 divided by 3 evenly. Now, what's the next number after 8 that will divide by 3 evenly? 9, yes? How far am I away from it? 1. So I need to multiply the top and bottom by the cubed root of y. That's what we need to do to get to the answer. been too long since the corny jokes. And we multiply the top and bottom. The top, we'll just have x times the cubed root of y. And in the denominator, well, we'll have the cubed root of y to the 9th. And if we simplify the cubed root of y to the 9th, we're really just dividing 9 by 3. 9 divided by 3 is? So we have x times the cubed root of y over y cubed. Any questions on this here? So we have 3 left. Number 31 is exactly the same as what we just did, but instead of having the cubed root of y to the 9th, we now have the cubed root of y to the 13th. So we're still going to use the cubed roots. We're still going to have y squared. Because again, we're looking for the next number after 13 that is divisible by 3, and that would be 15. Because 15 divided by 3 would give us 5. And if we multiply these here, well, the numerator would give us x squared times the cubed root of y squared. The denominator would be the cubed root of y to the 15th. And well, the cubed root of y to the 15th would be y to the 5th. And that right there would be the final answer. And whenever we do this method here, whatever we're multiplying, the exponent inside, so the exponent here would be 2, or y squared. That 2 can't be bigger than the root. It can, but that just means we're multiplying by a whole y on top and bottom extra above what we actually need. And the last one over here. Almost. We're looking at the cubed root of 27y to the 9th. Can we take the cubed root of 27? And it is 3. Cubed root of y to the 9th. Because we're really just dividing that 9 by 3, or we're multiplying it by 1/3. Because that's our rational exponent, which is gives us 3y to the 3rd. And that's it. Questions on this here? We do have this last one here. We want to simplify these here. Now, to be able to add or subtract, we need this term and this term here to be the exact same so we can subtract our numbers. And we can use both of them to kind of hint off of each other of what we need to get to. And this here, p to the 6th will actually work out to be p times the 4th root of 3p squared, 3p squared, 4th root, minus 48 will actually be our 3 times 16, and 16 would be 2p, 4th root of 3p squared, and this subtracts to 14p times 4th root of 3p squared. There isn't any homework assignment with this here. Y'all have a good rest of your day.